All right. Now let me talk a little bit about a different topic. We're going to only very briefly review lossy transmission lines. Lossy transmission lines are not going to be of great help in this class, but I do want you to understand what happens when you have a little bit of loss and where you have to be careful. First of all, let me remind you, based on the equivalent circuit that we discussed, that loss comes from primarily two areas. It comes from the conductor loss, meaning it comes from the fact that when you build a line, you use real-world metal, so it doesn't have infinite conductivity. But it also comes from dielectric loss, which means that the dielectrics that we're using are not perfect, but they're a little bit conductive. So when that happens, the telegrapher's equations will take this form here. So in addition to j omega L that we had before and j omega C, we also now have R and G. So the telegrapher's equation will become a little bit more complicated, and that means that the wave equations for the voltage and the current will become more complicated in the sense that now the propagation constant gamma is not just J beta, it's not just this imaginary number, but it has a real number here as well. So gamma is now a complex number and is clearly shown explicitly by this equation here. And because gamma is a complex number, the waves have not just a phase constant beta, but they actually have an attenuation constant alpha as well. So this e to the negative gamma g, for example, is equal to e to the negative alpha z times e to the negative j beta z. So now as the wave is propagating down the line, it doesn't simply change phase. In addition to that, it will basically change the amplitude, and it's this attenuation constant alpha that will make the power decay as it propagates through the line. One different way you can see exactly the same effect is by computing the characteristic impedance of the line by essentially calculating the V0 plus by I0 plus. And if you do that, you will find that the characteristic impedance of the line is also now a complex number. So in other words, in real world, it's impossible, theoretically speaking, to get a real impedance Z0. It will always be complex. But as we'll see in a second, if we have a low loss case, then Z0 is approximately real. So there are some conditions that need to be satisfied to make what we call the low loss approximation. And essentially, it means that R must be much less than omega L, and G must also be much greater than omega C. If you can satisfy those conditions, then essentially we have the low loss case, which is by far the most practical case, since in real life, low loss is necessary when we discuss transmission lines. So this is the one that has essentially the most interest. And there are some approximations that you will see here that gives you the approximate quantities of the attenuation constant alpha, phase constant beta, phase velocity v, impedance Z0, and wavelength lambda. The attenuation constant alpha, for example, will be expressed in this, with this equation, and is actually measured in Neppers per meter. And what you will also see here is that all the others constants, beta, v, Z0, and lambda, are equal to the case of lossless transmission line. So you basically have a same as lossless approximations for everything else except for alpha. So what you can take away from here is that when you have a transmission line that is low loss, you can basically use all the theory that we have done before, except that now you have to assume that you have an attenuation constant for the wave. I'm going to leave it at that. The book has a lot more information on this, but as I mentioned before, we're not going to be concerned too much here about lossy lines, but I did want to give you a flavor of what happens in this case.